Here is a number. The average person has slightly fewer than 2 arms. That is technically true. A small number of people have lost an arm and almost nobody has 3, so the average dips just below 2. And notice what just happened. A perfectly correct statistic described almost nobody in the real world. That is the strange power of statistics. Done well, it reveals the truth hiding inside a pile of numbers. Done carelessly or dishonestly, it can make a lie sound like a fact. Most people think statistics is about memorizing formulas for a test. It is not. Statistics is really about one thing: turning a messy heap of raw numbers into a clear, honest picture of what is going on, and then being sharp enough to spot when that picture is fooling you. And the second half matters just as much as the first, because you are shown statistics every single day, in the news, in ads, on social media, and most of us were never taught how to read them. I am Daniel, and this is Simplex Academy, where we take ideas that usually feel impossible and make them simple from the ground up. So let us rebuild statistics from zero, starting with the most basic question of all. What is it even for? Begin with the difference between 2 words people use as if they mean the same thing: data and information. Data is just raw values. Imagine I hand you the individual heights of 1,000 people, one after another. That is data. It is technically complete, but it is useless to your brain. You cannot hold 1,000 numbers in your head or feel what they mean. Information is what you get after you organize and summarize that data into something a human can actually understand. Statistics is the bridge between the two. It takes the overwhelming pile of data and squeezes out the useful information. That is the whole job. But before you can trust any summary, you have to ask where the numbers came from. This brings us to 2 words that quietly decide whether a statistic is meaningful at all: population and sample. The population is the entire group you actually care about. Every voter in a country, every customer of a company, every person with a certain condition. The problem is that measuring an entire population is usually impossible or far too expensive. So instead, we measure a smaller group taken from it, and that smaller group is called a sample. We study the sample, and then we make a careful guess about the whole population from it. Here is why this matters so much. A sample is only trustworthy if it fairly represents the population. If you want to know how often the average person exercises, and you only survey people you meet inside a gym, your sample is broken before you begin. You will conclude that everyone works out constantly because you only asked the people who were already there. That is called a biased sample, and it is one of the most common ways statistics goes wrong. So the first question to ask about any statistic is simple. Who did they actually measure, and were they a fair slice of the group in question? Size matters here too. If you ask 10 friends their opinion, pure chance could make them all agree, and you would learn almost nothing about the wider world. Ask 1,000 people chosen randomly, and the results will sit much closer to the truth about the whole population. 2 things make a sample trustworthy. It should be big enough that luck cannot dominate, and it should be random, meaning every kind of person had a fair chance of being picked. A small or hand-picked sample is where a huge number of misleading statistics quietly begin. All right, say we have a good sample. Now we want to describe it, and usually the first thing we reach for is an average, a single number that captures the center of the data. But here is what school often skips. There is more than one kind of average, and they can tell different stories. There are 3, and they are worth knowing by name: the mean, the median, and the mode. The mean is the one you already know. You add up all the values and divide by how many there are. Take 5 test scores, 70, 80, 80, 90, and 100. Add them, and you get 420. Divide by 5, and the mean is 84. The median is different. It is simply the middle value when you line all the numbers up in order. For those same 5 scores in order, the middle one is 80, so the median is 80. And the mode is the value that shows up most often. 80 appears twice, and everything else appears once, so the mode is 80. 3 averages, 3 slightly different pictures of the same little group. Now, why would anyone need 3? Because sometimes the mean, the famous one, quietly lies. Let me show you the classic example. Picture 10 people sitting in a room. 9 of them earn about $40,000 a year. Then a billionaire walks in and sits down, earning $100 million a year. Now calculate the mean income of the room. It rockets up to over $10 million each. Technically correct and completely absurd. Not a single ordinary person in that room earns anything close to $10 million. The median, on the other hand, the middle value, barely moves. It stays right around 40,000, which honestly describes almost everyone there. So when someone quotes an average and it feels wrong, ask which average they used. A single extreme value, pulling the mean far from reality, is one of the oldest tricks in the book. Let us pause for a quick recap, because you have already gained a real superpower. Statistics turns data into information. Any statistic is only as good as its sample, and an average is a single summary that can either reveal the center or hide it, depending on which average you pick. If this is starting to change how you read numbers, that is exactly what this channel is built for. So consider subscribing to Simplex Academy. Hard topics, explained from zero, without the fluff. Okay, let us keep sharpening this. A center number alone is never the full story, because it says nothing about how spread out the values are. Two groups can share the exact same average and be completely different. Imagine two classes that both average a score of 80. In the first class, almost everyone scored between 78 and 82, tightly bunched. In the second class, half the students scored 60 and the other half scored 100. Both classes average out to 80, yet they are completely different rooms. The simplest way to capture that spread is the range, which is just the largest value minus the smallest. In our test scores from before, 100 minus 70 gives a range of 30. Range is rough, but it instantly tells you whether the data is calm and clustered or wild and scattered. Once you care about spread, you naturally start picturing the whole shape of the data, and that shape has a name, a distribution. A distribution just shows how the values are spread across their range, how many land low, how many land high, and how many pile up in the middle. The most famous shape is the bell curve, sometimes called the normal distribution. Think about human height. A few people are very short, a few are very tall, and the vast majority cluster around the middle, which makes a smooth hill shape, tall in the center and tapering off on both sides. Once you can picture the distribution, a single average stops being a lonely number and becomes the peak of a shape you understand. And this makes it easy to talk about a word you have definitely heard: an outlier. An outlier is simply a value that sits far away from all the others, like our billionaire in that room. Outliers are not automatically errors, and you should not just delete them. Sometimes an outlier is the single most important point in the whole dataset. But you do need to notice them, because as we saw, one outlier can yank the mean around and quietly distort your conclusion. Now let us shift from describing data to measuring uncertainty, which is where percentages and probability come in. A percentage is just a way of describing a part out of 100. If 1 in 5 people prefer something, that is 20 out of 100, or 20%. Probability takes that idea and points it at the future. Probability is the long-run chance of something happening. When we say a fair coin has a 50% chance of landing heads, we do not mean it politely alternates. We mean that over very many flips, about half will come up heads. Any short streak can look lopsided. The pattern only appears across the long run. That distinction protects you from a lot of bad thinking, like believing a coin is due for heads after 5 tails. It is not. It has no memory. Percentages hide a trap of their own that catches almost everyone. Say an investment drops 50% in a bad year, then rises 50% the next year. It sounds like you are back where you started. You are not. Start with $100. A 50% drop takes you down to 50. Then a 50% rise adds only half of 50, which is 25, bringing you to 75, not 100. The percentages looked like they canceled out, but they were taken from different starting amounts. So whenever percentages are added, subtracted, or stacked together, slow down and ask a percentage of what. Here is one of the most important ideas in all of statistics, and the one most often abused. Correlation is not causation. Two things are correlated when they tend to move together. When one goes up, the other tends to go up as well. But moving together does not prove that one causes the other. The classic example: ice cream sales and drowning incidents rise and fall together across the year. So does ice cream cause drowning? Of course not. A hidden third factor, hot summer weather, drives both. People buy more ice cream and also swim more when it is hot. The two are linked, but neither causes the other. So whenever you hear that two things are connected, pause and ask the crucial question. Could something else be causing both? That single habit will make you dramatically harder to fool. And people will try to fool you, often with pictures, which brings us to misleading graphs. A graph is supposed to make data honest and clear, but the same data can be dressed up to scream or to whisper. The most common trick is the truncated axis. Suppose a value rises from 100 to 102. That is a tiny 2% change. On a graph whose vertical axis starts at 0, that bar barely grows, which is the honest picture. But start that same axis at 90 instead of 0, and suddenly the bar appears to tower over the other, making a trivial change look like an explosion. The numbers did not change. Only the frame around them did. So when a graph shocks you, glance at the bottom of the axis first. If it does not start at 0, be suspicious. There is one more quiet trick, and it is about what you are not shown at all. Sometimes, the most important data is the data that is missing. Picture a course that proudly advertises how much money its graduates earn. It sounds impressive until you realize you are only hearing from the people who finished. Everyone who signed up, struggled, and quit was silently dropped from the numbers. You are seeing only the survivors. This shows up everywhere. Product reviews mostly come from people who felt strongly enough to write one. So, on top of asking who was measured, always ask the sharper question: who or what got left out? Let me tie this together with the kind of claim you meet in the real world. Imagine an ad that says a product is proven to make people 90% happier. It sounds powerful, but you now have the tools to interrogate it. First, who did they measure, and how many? 90% of 10 hand-picked fans is meaningless. Second, happier compared to what? Compared to doing nothing or compared to a rival? Third, is happiness even something you can measure cleanly, or was it a vague survey? And fourth, is there a real cause here, or just two things that happened to move together? A confident-sounding number falls apart fast the moment you ask how it was actually made. So let us gather the mistakes to avoid into one place. First, trusting a sample without asking who was in it. Second, accepting an average without asking which one, especially when a big outlier is lurking. Third, staring at a center while ignoring the spread and the shape. Fourth, treating correlation as proof of cause. And fifth, believing a graph before checking whether its axis starts at 0. Notice that not one of these requires heavy math. They just require asking how the number was born. Now, a fair and honest word about what statistics cannot do, because this matters. Every summary throws away detail on purpose. That is the point of a summary, but it means a statistic describes a group, never a specific individual. The average tells you nothing certain about any single person. Statistics also deals in patterns and probabilities, not guarantees. It can tell you what is likely across many cases, not what will definitely happen in one. And it can be completely accurate and still mislead if the sample was biased or the picture was framed to deceive. Statistics is a tool. Like any tool, it can build or it can trick, and knowing the difference is the entire skill. So let us bring it home. Statistics is not a pile of formulas. It is the craft of turning raw data into honest information and the shield that keeps that information from lying to you. You describe data with its center, its spread, and its shape. You judge any statistic by its sample. You remember that averages can hide, that correlation is not cause, and that a graph is only as honest as its axis. Master those few ideas, and you will read the numbers around you with a clear, calm, skeptical eye, which is a genuinely rare and powerful thing. So tell me down in the comments, what is a statistic or a headline that always confused you or felt misleading, and I might break it down from zero in a future video. And if this finally made statistics feel simple and useful, subscribe to Simplex Academy. I am Daniel, thanks for watching, and I will see you in the next one.